Okay, I'm doing this important lesson just before the test to help you with a bit of algebra. It's one thing with being away from school. I've got to be careful. I'm not going to get the chance to talk about these important lessons that are not necessarily in the book, but they're just little things like good habits. So the name of this lesson is "Don't expand brackets unless you have to," or that's its subtitle. Okay, and to demonstrate this, um, we're going to consider a function like this: f of x equals x minus 2 cubed times x plus 4. And you can see over on the right of the screen, it's graphed there for you. So it is a quartic. You've got a cubic factor and a linear factor. Okay, so if we were doing some algebra with this and we wanted to find f dash of x, we might think what a great idea it would be to expand it. Well, I hope you don't think that, because expanding a cubic's hard enough, and then having to multiply it by another linear, that would be a nightmare. So I'm sure you wouldn't, but we'll do the product rule here. So we'll, first of all, treating this as the u and this is the v, first of all we differentiate the first factor and leave the second factor alone. And then we leave the first factor alone and differentiate the second one. Now, the second one here is just x plus 4, so our v dash is just 1. There's the product rule, just in case you forgot it. Okay. Now, this is actually the point that the whole lesson is about. Okay, this next bit. We're going to imagine we've got a lot more to do. Imagine we want to find station points, and in fact, we're going to refer to them in a bit later. We might now again be tempted to expand things out. No, you've got two common factors. Okay, so you've got x minus 2 as a common factor, and better than that, you've got x minus 2 squared. Okay, so take that out as a common factor. Whatever we haven't taken out on this term here needs to go inside this big square bracket, so we haven't taken out the 3 and the x plus 4. And over here we'd have another x minus 2. Now I've left the brackets in. Okay, you could have expanded that, but I like to be careful. So here in this square bracket we've got 3x plus 12 plus x minus 2. Okay. And then simplifying this, we've got 4x plus 10. And quite often you'll find there is a factor you can pull out of this one bracket here. And in fact, you can see you can pull out 2. So we'll put 2 at the front. We've taken 2 from here, so 2x plus 5. Okay, now given this is f dash of x, okay, this would mean we have stationary points at x equals 2 and this is negative 5 over 2 or negative 2.5. And I think if you do go over there, you'll see here's the one at 2 and here's the one at negative 2.5. Okay, so I think what I'm going to do is make a part 2 of this video because I've not given myself too much room. Okay, so we'll do a part 2 and we'll have a look at the second derivative. But it's going to be essentially the same thing. Oh, that should have been squared, that factor. Okay, there at x minus 2. And note that does match the fact that it's a flat sort of touching point there at that point x equals 2. So yeah, that was a small error there. Okay, on to part 2. Do you know what? I've had to think about it and I'm going to try anyway to fit it in. So the second derivative. Okay, let's squeeze this in. It's the same process. Okay, it might actually be a little bit easier. So we'll differentiate the first factor. So 4 x minus 2. Leave the second factor alone. 2x plus 5. Okay, then plus, and then we've got 2x minus 2 squared. And then out of this, when we differentiate this factor, we'll have an extra 2. Okay. Yeah, we can just about see that. Okay, so this time now we've got the x minus 2 of a factor, and in fact we've got 2 times 2 is 4, so we might as well pull out the 4 now because we've got 4 and x minus 2 as a factor. Yeah, there's the 4 there, and also I've got 4 here. Okay, square bracket, and in the square bracket I need the 2x plus 5, and over here one more x minus 2. Yeah, this takes a bit of practice, but hopefully you can see if you multiply this by this, you get that big term, and this by that, you'll get that term. Okay. Right, so I'm always very disciplined when I do my maths, okay, because I've been doing this a long time and I make a lot of mistakes. Okay, so this is why I sort of go through this long process of, square brackets, brackets inside brackets. I just don't like making mistakes. They cost us marks. So anyway, in here, in the square bracket, we've got 3x, and then we've got plus 3. And you see again it's happened. You can pull out a 3 from here to make 12 at the front and x minus 2. A lot of people get confused thinking, oh, I'm taking 3 out of here, I've got to take 3 out of here as well. No, you don't. Okay. Alright, so that's x plus 1. So what this should mean, okay, this should mean that we have points of inflection, because this is our second derivative, points of inflection, and I can just squeeze it on at x equals 2 and x equals minus 1. Okay, so let's have a look to see if that's true on our graph. This is why I draw the graphs first. So we've got the point of inflection at x equals 2. That's obviously stationary. It's obviously stationary, and we've proved it's stationary because 2 is also, it is a stationary point, f dash of x. It came up as a factor here and as a factor here, so we know that's a stationary point of inflection. And down here, our other one is at minus 1. Oops, yep, did I say? Yeah, no, I did say minus 1. At minus 1, x equals minus 1. There's our other point of inflection where the curve is going from concave up to concave down. Okay, and we know that's not stationary, apart from it doesn't look it. It wasn't a stationary point. Okay, so this is a very important example. But the main point was, don't expand brackets unless you have to.